Hello, the subject of this lecture is dead loads. Let's go ahead and get started. You can find material covering dead loads in both the Tally textbook and in the Fenella textbook, and it happens to be in Chapter 3 of both of those texts. With respect to dead loads, review sections 3.1, 3.2, and 3.5 out of Tally, and sections 3.1 and 3.4 out of Fenella. Dead loads are covered in section 1606 of the International Building Code, but basically that section just refers back to chapter 2 for a definition of what dead loads are. That definition basically says that dead loads are the actual weight of the construction materials and the fixed service equipment that are attached to or supported by the structure. Dead loads are covered in ASCE 7, Chapter 3, along with soil loads and hydrostatic pressure. And the definition of what a dead load is, according to ASCE 7, is almost identical to what you would find in the International Building Code. There is a commentary to Chapter 3 of ASCE 7 that's quite helpful, though. In fact, there's a table, Table C3-1, that provides the various design dead loads it would use for various types of construction, different construction components. This shows an excerpt of that table. The actual table itself is several pages long, and I'll include it in the PDF version of this presentation that's posted online. Also included in the commentary to Chapter 3 of ASCE 7 is a table that provides common material densities for materials that are used in construction. It's important to bear in mind, though, that these weights of these construction materials can vary, so it's a good idea to verify them as part of your design process. And there's a note that says that in cases where information of dead load is unavailable, then you must get approval of the building code official in order to use those weights. And this slide provides an example of what that table C3-2 is going to look like. Some common material self-weights that we use in structures. Water's about 62 pounds per cubic feet. Soil has a weight depending on the type and the how moist it is. It's between 63 and 120 pounds per cubic foot. Reinforced concrete is typically taken as 150 pounds per cubic foot, and structural steel has a weight of 490 pounds per cubic foot. Dead loads are generally modeled as area loads. Pounds per square foot would be a typical unit. They're often based on the material and equipment that you expect to be in your structure. And as far as the structural weight would be concerned, you're talking about the floor or the roof deck, the weight of the floor or the roof joists, the weight of the girders, the columns, and the facade. In terms of machinery and equipment, you would include plumbing stacks and risers, HVAC equipment, elevators and machinery, fire protection systems, and also architectural details like floor coverings, ceiling coverings, and things of that nature. This is an example of a page out of the Volcraft floor decking manual. And this would be typical of the type of decking that would be used for a floor in a steel frame building. So we have metal decking that's supported by, we have concrete that's supported by metal decking that would be in turn supported by the floor joists. And this table provides a lot of information. We'll revisit it later in the semester when we talk about the design of metal decking. But for right now, what you would take away from this is the self-weight of the deck. So for a 3-inch VLI decking filled with 5 inches of concrete, you would have 45 pounds per square foot if it was normal weight concrete, or 35 pounds per square foot if it were lightweight concrete. And this is where you would go to determine that. If it were a reinforced concrete floor deck, then it would probably be monolithic. In other words, it would have a constant thickness, and then you could just figure out the self-weight of that concrete. And there are some examples in the Tally textbook that show how to do that. Okay, it's not just the weight of the floor, though. There's also superimposed dead loads or super dead loads that include the weight of the, say, lighting fixtures, ductwork for the air handlers. You have a sprinkler assemblies, and then, of course, the weight of the architectural items like the ceiling panels and things of that nature. That all has to be supported as well and is considered part of the dead load. Okay, let's take a look at an example problem. Let's assume that we have a structure that has 30 foot by 24 foot bays and a story height of 14 feet. Let's suppose that we have Volcraft 3-inch VLI metal decking with 5 inches of normal weight concrete. We have W16 by 40 floor joists spaced at 6 feet center to center. We have W21 by 55 girders in the short direction, so they would be spaced at 30 feet. We have W14 by 90 columns, and we're going to design for a mechanical load of 12 pounds per square foot and an architectural load of 15 pounds per square foot. If we do the math on this, what we would find is from the Volcraft manual that the decking in the concrete has a weight of 45 pounds per square foot. The floor joists are 40 pounds per linear foot, spaced at 6 feet, so they would be 6.67 pounds per square foot. The girders have a weight of 55 pounds per linear foot, spaced at 30 feet, so they have a self-weight of 1.83 pounds per square foot. We have columns that are 90 pounds per linear foot, and we have two of them attributed to each bay. And the bay has an area of 30 feet by 24 feet, so the columns would have a weight of 3.5 pounds per square foot. And then finally, when you consider the HVAC and the architectural, we end up with a total dead load, in this case, of 84 pounds per square foot. Okay, dead loads are often estimated to be larger than what is actually present. This isn't, at first, doesn't seem like a bad idea. If you think you're going to get 84 pounds per square foot and you design for, say, 150 pounds per square foot, you might walk away thinking that you were being conservative. However, it's important to bear in mind that sometimes the dead load acts as a restraining force. If you consider the overturning force of the wind or a seismic action, then the dead load actually helps resist the structure from toppling over or from sliding. So if you overestimate the dead load, in some cases it might be unconservative. Okay, when we talk about roofs, they tend to be lighter than floors. So this is an example out of the same decking catalog from Volcraft, and it shows a typical roof decking. This is only 1.5 inches thick, 1.5 F, and you can see the dead loads range from 1.73 pounds per square foot up to about 2.8 or 2.9 pounds per square foot, depending on the gauge or the thickness of the decking. And again, we'll come back and talk about the design of metal decking later in the semester. But for right now, just bear in mind that we're dealing with a lighter decking element for the roof systems. Here are a couple of examples of common roof details. On the right, you can see a steel frame building where you have some type of a metal decking that is supporting rigid insulation board, rigid fiber board. And it's showing two layers, maybe each of those layers is 2 inches thick. And then you have some type of water barrier above that. And not shown in the figure is a ballast or a gravel. You often put ballast or gravel on the top of the water barrier to provide resistance against uplift. Without that, the wind would blow across the roof. It would create an upwards lifting action, uplift, and it could pull the rigid insulation board off of the roof, or it could actually provide enough uplift force to pull the roof framing off as well. So we add gravel to that to provide ballast to keep the roof from coming off. It also provides a layer for UV protection for some of the bituminous moisture protection that's used there. On the left is shown a typical reinforced concrete roof building, a roof system for a reinforced concrete building. And in this case, you would probably use reinforced concrete decking instead, but the rest of it is similar in nature. Then here are two sections corresponding to those two roof types. And this comes out of the Building Construction Illustrated by Ching. So again, roof deck concrete on the left, roof deck metal on the right, but then you have some type of insulation board providing support to the roofing membrane, and then the gravel ballast on top of that. So if we consider a roof system in a steel frame building, we'll go with the same base spacing, same story height as before. Now we have a Volcraft 1.5F 18 gauge metal deck with 4 inches of fiberboard insulation on top of that, and then that would be supporting gravel covered bituminous membrane. We're going to assume that we have 16K2 bar joists in the long direction instead of using a W shape. And then we have W18 by 40 girders in the short direction, supported by 14 by 61 columns. And our HVAC load is a little less. Instead of 12 PSF, we'll take it as 8 PSF. And the architectural is also going to be lower. Instead of 15 pounds per square foot, we'll take it as 5 pounds per square foot. Because the roof would be supporting a ceiling below it, but presumably would not be supporting any flooring above it. So we do some math here. If we look up the decking in the fiberboard, we would take 2.74 pounds per square foot for the decking out of the Volcraft manual. Out of the table in the commentary to Chapter 3 of ASCE 7, it gives us a self-weight of the fiberboard is 1.5 pounds per square foot per inch. Then we take the gravel and the membrane, again, out of the commentary to ASCE 7. I'll use 5.5 pounds per square foot. Out of the catalog from the bar joist manufacturer, that particular bar joist has a weight of about 3.5 pounds per linear foot. So it's spaced at 6 feet. That would correspond to a self-weight of 0.58 pounds per square foot. The 18 by 40 girders are going to correspond to a self-weight of 1.33 pounds per square foot. The W61 columns give us 2.37 pounds per square foot. And then the weight of the HVAC and architectural elements give us a self-weight of 13 pounds per square foot for a total of 31.5. Okay, not all roofs are created equal, however. This is, of course, the roof to Zimmer Auditorium, and this would be a roof that has a much higher self-weight than the roof that we just illustrated. In the design of this roof system, you would have to consider the weight of the soil, the weight of all of the landscaping elements, including the trees and the grass and the shrubs. Plus, you have the weight of all of the paving stones in there as well. And then there would also be a live load on this roof that we'll discuss in the next lecture. So at this point, we'll turn our attention to self-weight of facades and curtain walls. And there are a lot of different ways to detail these. And the way that the loads enter our structure depends a lot on how they're detailed. Basically, the facade or the curtain wall of a structure is there to provide the inhabitants or occupants of a building from the elements. They provide protection from the cold in the winter. They provide protection from the heat in the summer. They provide protection from the rain and the wind and the snow. In some lower rise buildings, the weight of the facade might be supported directly on the foundation, like we're illustrating in this particular slide. You can see the weight of the brick veneer. Masonry veneer is supported directly by the foundation, so the structure itself doesn't have to support the weight of the facade. In this case, the substructure supports the weight of the facade directly. The veneer is tied to the structure, so when we consider seismic action, then the structure has to support the lateral load imposed by the mass of the veneer. But the structure in all other cases is just there to support the veneer from toppling over. The weight of the veneer itself is supported by the foundation. Okay, here's an example of a facade or curtain wall system that's supported by the structure itself. So this is a reinforced concrete frame. You have a spandrel beam there that's illustrated, and it has some type of a metal attachment embedded into the concrete that then supports a ledge angle, and that ledge angle supports the masonry veneer. So this would be a case where you would have some type of a masonry facade that is supported directly by a concrete frame. Similarly, here is a masonry veneer that's supported by a steel frame. So in this case, working from the outside in, you have the masonry veneer that is supported by a ledge angle at the bottom. Steel framing is called out there, steel angle. That steel angle is supported by a framing angle that comes in at the underside of the spandrel beam, and then there's an angle at an angle that is often referred to as a kicker that provides lateral support for the ledge angle that's supporting the masonry. So two different options, one for concrete and one for steel. When we look at steel structures and how the facades and curtain walls are attached, there are numerous options available, from directly attaching the facade or the curtain wall to the concrete deck, from attaching the curtain wall to the spandrel beam, or providing attachments directly at the column locations. This picture here on the right shows an example of a structure in the Cincinnati area where the facade attachments are part of the steel structure and they're attached at the column locations. So this is a corner column, and these two tube attachments here are in place for the curtain wall to be attached at a later time. This is another example. This is a structure in Fairfield where the ledge angle here at the bottom. So let's see, this is the ledge angle right here, and it is being supported by these drop down angles and then attached to the spandrel beam. But there is also a kicker here that comes back to the column to provide lateral support for that. So the way that the facade load enters the building depends a lot on how it's attached, but one common way of going about getting these loads into the structure is to define a tributary width. So let's assume that we have a first floor is right here and the roof level is right there. We might define a tributary width or tributary height for that first floor like this. So that would be the tributary height, call it T sub H. Take the unit weight of the facade in terms of some pounds per square foot, multiply by the tributary height, and you get a load in pounds per linear foot that could then be applied to that first floor spandrel beam like that. Okay, the same concept can be used for the roof level as well. So this would be the tributary height for the roof level, and multiply the unit weight of the facade in pounds per square foot times that tributary height, and you can apply that as a line load to the spandrel beam in the roof. Okay. Alternatively, you could apply these loads as point loads. So here's a tributary area that would be contributing to the load that's applied directly at that point. And one thing to bear in mind is that when you corner columns, you have a tributary area not just from the one face, but you have a tributary area from the adjacent face as well. So both of these areas would contribute to the point load that would be applied to that column. All right, this slide shows some common facade and curtain wall materials that are used, anywhere from aluminum to glass to several types of masonry and stone. So just take a 12-foot story height as an example. You could have a facade that imposes a weight of 64 pounds per linear foot, all the way up to 700 pounds per linear foot, depending on the type of facade that you're going to have. Now, obviously, you couldn't have a solid granite facade. Most people like to have windows in their buildings, so looking at 660 or 690 pounds per linear foot is a bit excessive. If you cut windows in there, that would obviously reduce that weight to some extent. Okay, so I want to close out by saying a few words about soil pressures. I'm not going to discuss this very much. It is very much the topic of a geotechnical engineering class, but just a couple of slides on this. 3.2-1 of ASCE 7 gives us some weights of the soils that can be used for lateral pressure design in the absence of any better information. And so what they mean basically is if you don't have a geotechnical engineering report and you need to design for something, then use these as minimum loads. So it gives you a list of different types of gravels, different types of soils, clays, etc. Depending on what type of soil you have, you multiply the number that's given here by the height of the soil, and that gives you the magnitude of the lateral pressure. So if we were going to deal with let's suppose we had a poorly graded clean sand, then we would design for 35 pounds per square foot. And if we were looking at a retaining wall structure like the one that's shown here, we would multiply 35 pounds per square foot times the height of that wall in order to get the magnitude of that loading down here at the bottom. Okay, we also need to consider the presence of water if it's there. If you have water there, then you design for the hydrostatic pressure as well. But bear in mind that when water is present, it actually it reduces the weight of the soil by providing buoyancy for it. Okay, the lateral pressure might also need to be increased if you have expansive soils like clays. When clay gets wet, it tends to expand in volume. That expansion would cause a pressure against the wall that needs to be accounted for. And also bear in mind that the lateral pressures can be increased if you have a surcharge loading. So if you park something large on top of that soil, then that increases the lateral pressure that you would have to design the wall for. Okay, that brings us to the end of this presentation. Hopefully you have an idea of what dead loads are and how they're calculated, and just a taste of lateral soil pressures in there as well. All right, thanks.